Morning, everyone. Welcome to the PhD difference for today. Welcome to Daniel, who will give his lecture defending his work for the past 3 years. It will be very interesting, and Daniel handed in his PhD around developing manufacturing systems, platforms. The faculty has appointed a committee to evaluate the work of Daniel. So I would like to welcome Professor Mats Jackson from Jönköping University, Sweden, and Associate Professor Arne Billberg from the University of Southern Denmark. So my name is Simon Bø. I will be the moderator for today. I'm also the chairman of the committee. Soon I will sit down and listen to Daniel. And then later on we will have questioning. So the faculty, on behalf of the faculty, I would like to give my gratitude to the committee, the big work they've done in evaluating Daniel's PhD. So the procedure for today is that Daniel will now give a lecture on his work for 45 minutes, no longer, hopefully. And then we will have a short break. Then we will reconvene at 11 o'clock for the questioning for a maximum of 2 hours. If there are any questions from the audience, please direct them to me in the break. Then you can ask them to Daniel afterwards. After the questioning will end at 1 o'clock, there will be a reception in our common room in Fibegastræde 14. So with no further ado, I will leave it to you, Daniel.
All right. Well, thank you. Yes, so welcome everybody here today. I'm very pleased to see so many people here. I've really been looking forward to this and to actually telling you all about what I've been doing. Because I have been talking to people about what I've been doing, obviously, but this gives me 45 minutes of uninterrupted talk. So yeah, let's get on with it. But the title of the presentation today is Developing Manufacturing System Platforms. And I hope you enjoy it, basically. The agenda for today is fairly simple. We've got 4 sections to go through. The first one is basically setting the stage for the entire presentation and for all of my research. So that means I'm going to introduce you to the various concepts and the basic foundations for what I've actually been working on. So introducing you to the concepts and the context and the challenges and the motivations that I've for why I've been doing this work that I have. Afterwards, we're going to move into framing the research, where I'll talk a little bit about my objective and my overall purpose in a more formal manner. And I'll describe the actual approach that I've taken, the research approach I've taken, and then I'll move on to introducing the actual case, company, and some of the specific research questions I've been addressing. After that, we'll move on to the actual contributions that I've made within the field. So these are the things that I've actually done besides gathering up a whole lot of knowledge. I've made some contributions as well. This is what I'll tell you about in section 3, and then, of course, round off with some concluding remarks, a little bit about future research, and some acknowledgements as well. But yeah, let's head on into it to actually setting the stage. And this includes basically what I've been working on, why I've been working on this. And when people ask me what I actually do, I usually just say that I work in manufacturing or in production. And depending on the reaction, I can sort of gauge where I have to start based off of that. And it's still somewhat tricky to describe what it is that I actually do, at least with an elevator pitch of 1 or 2 minutes. It's a little tricky. But today I've brought a lot of visual aids as well that should hopefully help convey what I'm talking about. But the key is that I do work in manufacturing, and knowing what manufacturing is fairly important to understand the rest of the work that I'm going to present. So that's why we'll start off with actually talking a bit about what manufacturing is. And at its core, manufacturing is actually just the transformation of an input into an output. And these kinds of transformations, these transformation processes, they actually happen all around us constantly. They both occur naturally, or they are something that we can manipulate as humans in order to get to a certain end result that we desire. And this particular kind of transformation process that that we manipulate to get to where we want to. That's what we call a manufacturing process. And these manufacturing processes take an input in the form of materials or components, and then they transform them into some parts or products, basically. And an example of this can, for instance, be the end result that we want out of this is a set of Lego bricks or a collection of Lego bricks of various colors. When in order to get there, we need an input. In this case, our input is a set of polymer granules. And these polymer granules are basically plastic pebbles, fairly small. We put those into an injection molding machine here. We heat it up. We put them into an injection mold, basically, and then we cool it down, and then we have our final Lego bricks afterwards. So the actual injection molding machine, that's the equipment that carries out our manufacturing process, while the actual process itself is the heating and the cooling and the shaping of our materials. And in some cases, like this, for instance, the injection molding machine is considered a somewhat advanced piece of machinery. There are obviously more advanced pieces of machinery out there, but there are also far simpler pieces of machinery. And these manufacturing processes, they can definitely be carried out by this kind of very advanced machinery, but they can also be carried out with very simple tools done manually. So for instance, when you assemble a chair with a set of screws and a screwdriver, for instance, that's also a manufacturing process, and it's a fairly simple one. But when we are looking at more complex products, we're going to eventually need more advanced machinery, more advanced techniques in order to get this level of quality that we actually desire of our product, and to actually be able to manufacture the product with the technology that it needs. And in certain cases, we'll also need more than just one transformation process, because one transformation process can transform one input into another output, but we might need to go more steps to actually get there in the end. And the multiple manufacturing processes in a certain sequence, that's what eventually leads us on to the actual manufacturing system itself. So the manufacturing system itself is essentially a sequence of manufacturing processes that are carried out in a specific order. And we need this specific order in order to get the product that we want. The way we usually describe this is with a manufacturing process flow, of which this is an example. These are just dummy processes. They don't actually mean anything. But this is a way to describe, for instance, the input, some handling processes, some inspection processes, and then the actual processes that are being carried out. So this might be the actual injection molding process and some assembly afterwards, for instance. But this is the way you describe the actual function of a manufacturing system, because the manufacturing system itself is very much tied to the physical entities as well. And that also means that each of these functions can be carried out in various different ways. So there are various different physical entities that can carry out a specific process. And that means we get a lot of different actually physical instantiations of manufacturing systems. They can look in a lot of different ways. So these are just a few examples of some of them. The one at the top here is a very integrated one, where we basically have a roll of metal that is with various operations being performed after it's been spooled out to get to our end product, which is some sort of new shape, new product. We have an assembly line here, which is a combined manual and an automated assembly line, where we have some automated movement of the actual car chassis, but we have some manual work done on it as well. And the last one over here is the manufacturing system that we have at our lab, right over in Fibikestad 14, so you can actually see that afterwards. But this one is specifically built with some fairly advanced technology in order to allow us to move things around in it and to change the actual capability of it. So this one, we can actually change the shape of ourselves, whereas the other ones are slightly more locked down. But the key is that the manufacturing system is actually just simply the physical equipment that carries out these operations that we actually need to finish our product, or to get the product that we need in the end. And there are huge varieties of these, and more or less complicated stuff, obviously, more or less complicated manufacturing systems. But why even work in manufacturing? Why even work with manufacturing systems? And there are a lot of reasons why, actually. So the statistics say, for instance, I'm not going to go massively into the statistics, but according to our statistics for Denmark, a lot of our GDP is actually generated through export, and a lot of this export is generated through manufacturing. So it is a fairly important field in Denmark specifically as well. We also have a lot of people employed in the manufacturing industry, and with increasing outsourcing, well, this number is starting to dwindle a bit, and we'd really like to keep manufacturing in Denmark as well, because we are actually pretty good at it, but we obviously want to be even better to keep the jobs here as well and keep all the industry in Denmark. And for the challenges and motivations that I've considered for manufacturing systems or for manufacturing in general, these are 5 broad categories that I've been looking into a little bit. I'm going to go through all of them very briefly, and then I'm going to focus on the one that I've actually been working on, which is the highlighted one here with individualization. But the demographic change, to start there, well, we're seeing people are living longer, obviously, that's a good thing, but that also means they're staying longer at the, they work for longer as well. That means that we have more supporting tech and more assistance that we need to, that the workers will eventually need. It also means that re-education will become more and more important in order to get people to work different jobs. As the jobs actually change, the job functions start to change. Well, then we need to re-educate them as well so they can carry out their tasks. Individualization, as I'll touch on afterwards, well, in just a second. Well, this is the increased variety that we're seeing because the customer demand is becoming increasingly varied. We're seeing more and more individualization, more and more changes to how the demand actually fluctuates. So people want to be, want products specifically tailored to their needs. We're seeing lots of new technologies coming on, especially with the ongoing fourth industrial revolution, for one. And with all this new technology, we need to somehow consider how can we use this technology, or how can we implement this technology, how can we accommodate all this new technology. And that means both the manufacturing technology itself, so the new manufacturing processes, but also the technology that goes into the actual products. We need to somehow be able to manufacture these. All of this also brings some security aspects in terms of privacy and security, because all these products are starting to be more and more connected. So these are also some things we need to consider. In terms of globalization isn't exactly new, but it's still ongoing and it's not slowing down either. So the physical distance is starting to mean less and less, and that means we have a bigger markets that we actually compete on. So we need to somehow remain competitive, and we need to take this globalization into account when we're talking when we're aiming our stuff at various kinds of markets. Sustainability is also becoming an increasing priority for the consumers, and thus it's becoming increasingly important for the actual manufacturers themselves as well. Because if it's important to the consumers, it has to be important to the manufacturers as well. And this also provides us with a lot of new challenges in terms of we have to start to reuse more and more. We have to have a green perspective or a green profile as a manufacturer in order to actually win the customer over. And we'll dive into individualization and customization a little bit as well, because we are, as customers, we are individuals, obviously. We all want to be perceived as individuals. We want products specifically tailored to us, because why bother actually buying a product if it fulfills a lot of needs that you don't actually have? It might only be a subset of the functions that it actually provides that you actually want. So that means you're buying something that's overkill, essentially, for what you need. And this has changed the way the market fluctuates. We have a very dynamic market now where we can see that we need a lot of different products, basically, and the demand fluctuates quite a bit. And that's quite a challenge to manufacturers. Usually the way you'd accommodate this individualization is by increasing the number of variants of a certain product. So we keep introducing new variants of products in order to accommodate the specific demands of individuals. An example of this is, for instance, the My Muesli case, where you can basically customize your box of muesli specifically to your needs. This can either be with a taste perspective, so you want it to taste a specific way, but you can also do it in a way that means that you get the specific nutrients that you need. So you can customize the box specifically for what you need for a healthy diet, the things you might be missing from your regular diet. Another example is for cars, for instance. So this is really happening all over the spectrum. So both from relatively small products to very large, heavily engineered products. But some of you might have checked out the configurators on car manufacturers' websites, trying to make up maybe your dream car, seeing how much that would cost, or what's the most expensive car you can actually get from this manufacturer, for instance. But this means that in these configurators, you can change the exterior, you can change the interior, you can change all the accessories, you can change some of the software applications that the car actually uses. And in certain cases, you can actually change the performance of the car as well. So this is really happening all over the spectrum, and it does have some consequences as well, because it's not that easy to just keep introducing new variants. We need to be able to respond to the demand quickly, so we need to introduce them quickly. We need to have relatively fast time to market, so that means from the concept introduction to the actual product is introduced to the market. We need to be quicker at that, to go from concept to production, essentially. So yeah, this increased individualization in particular that I've been looking at has had some quite significant consequences to the manufacturing industry. And that's actually what I'll get up to right now. Because we have something called manufacturing paradigms that we've been working with. And these are essentially terms that we put on the specific way that the manufacturing industry looks at a certain point in time. So this graph basically shows how the industry has changed based on the variety and the production volume. And the production volume is the amount of products that are being put out, essentially. So these are the number of products that we actually manufacture. But yeah, as we start down here in the 1850s, that's quite a while ago, but that's where we initially had craft production. So that means we had a very high variety, but we had very low production volume. And that's because the people who actually worked this craft production system and the people who actually manufactured the products, they're very, very specialized workers. So they honed their craft, they were actual craftsmen, they spent a lot of time specializing and learning their actual craft. But as essentially also the population grew, well, we started to introduce, we needed a higher production volume, and that moved us on to actual mass production era. And the mass production era was where we started to standardize more components of our actual products. We started to be able to manufacture these products much, much faster because of the standardization. So we started to replicate our essential products and started producing more of the same rather than making a unique product for every single person. And one of the things this is usually attributed to is actually the Ford Model T, where they built one of the very first automated manufacturing systems or production lines, where they had automated conveyors and a lot of people carrying out repetitive manufacturing processes in order to churn out a lot of near identical cars, basically. And this manufacturing paradigm is basically still in use today. We still see it also at car manufacturers as well. They have introduced a lot of new technologies to be able to manufacture more variety, because we are starting to see this trend towards decreased volume and increasing variety again. And what we're moving into now is actually the mass customization paradigm, essentially, where we have a collection of products that we basically want to be able to customize to as many people as possible. That also means that we want to be able to parameterize the actual needs or the actual features that we have. We need to be able to know exactly how we can change these features to fit various people or various groups of people, essentially. And in this case, for mass customization specifically, we want to be able to combine the economics of scale and with the economics of scope, whereas the economics of scale, that's what we've gotten from the mass production era here over here, where we are able to manufacture so many products that we can make them very, very efficiently. That's the economics of scale, whereas the economics of scope is basically introducing more variance in order to meet the demand. So we want to be able to combine these two and get the most of it as much as possible, at least. And for each of these paradigms, there are basically some types of manufacturing systems that work with each of these paradigms as well. These have been developed in order to be the most efficient within their specific paradigms. The two I'm going to be focusing on today are the dedicated manufacturing systems, which were developed for the mass production era. This is where we have a very low variety, but we have very high efficiency. So they're basically dedicated to a few product variants or maybe only one. Then we also have the changeable manufacturing. This is basically an umbrella term covering a number of manufacturing systems or that have various kinds of technologies. But this basically means changeable manufacturing, that we can change the manufacturing system to fit our specific needs. And changeable manufacturing is essentially what we're hoping to achieve with this whole work with manufacturing system platforms and everything. So just a little bit more about these types of manufacturing systems. The dedicated manufacturing system up here is very, very high efficiency, very high efficiency, very low variety. So very, very few variants, but we can produce a lot of them. And an allegory to this is, for instance, the ratchet ring wrench, which you can, it's suited for just one task, but it's very, very efficient at it as well. You don't even have to actually lift the wrench to actually carry on with your operation, but it only fits that specific type of nut or bolt. For the flexible manufacturing systems, we have comparatively low efficiency, but we have a high variety. So we can do a lot of different tasks, but it doesn't do any of them very, very efficiently. So we have a lower production volume output from these types of systems, basically. An allegory to this will, for instance, be the adjustable wrench. So you have to lift it every single time you make a turn, basically, but you can also adjust the actual wrench itself to fit a number of different bolts or nuts. And the reconfigurable manufacturing system has a very high efficiency and a very high variety, essentially. And an allegory for this is the socket wrench, because like the socket wrench, the reconfigurable manufacturing system allows us to change various components of the system itself. So we can exchange components of the socket wrench in order to make it fit the various things, and it's still very, very efficient at what it does. The same thing goes for the reconfigurable manufacturing system. And this might make it seem like the reconfigurable manufacturing system is the best solution in all cases. Essentially, that might not necessarily be true, because if you don't need the actual variety, why bother actually developing a reconfigurable manufacturing system if you only have one product anyway? So you still need to sort of scope in figure out what sort of changeability do I actually need, what sort of changes do I actually need for my manufacturing system. Because it does come with a high cost to develop this. It takes a lot of time. It's not easy to do. It's still not easy to do, but we're trying to get there, obviously, with all this research into reconfigurable manufacturing systems. And so these are just two of the types of changeable manufacturing systems that we're considering. And this is what I'm going to be talking about today as well. What we're hoping to achieve is basically these kinds of systems through platforms. And I mentioned platforms quite a bit, and now we're quite a few slides in, and I haven't actually told you what platforms are. But platforms are fairly simple. It's about locking down features in the product. So you ask these two questions, or answer these two questions basically. What in my product or what in my system can I actually change? What am I allowed to change? And where do I allow variety and where don't I allow variety? So that basically means we lock down some features so that we ensure that we can keep building these systems in the future, that we know that these systems or these products, they can keep working in the future. An example of a platform is, for instance, the Lego minifigure. So up here we see this is the base Lego minifigure from which we can develop all of these and many, many more Lego minifigures. And the reason they can do this is because they have locked certain things down with respect to the actual Lego minifigure. So for the helmet to work, we obviously need to know how the head looks, and for various tools and accessories to work with the hands, we have to know exactly how the hands look. And that's what they've done here in the patent. They've looked at the various characteristics of the Lego minifigure, and they have standardized certain distances, certain lengths. So for instance, the hand here is always the same diameter. And they have very, very tight tolerances to this because they know that they need to have this under control if it's supposed to work with all the tools. Because one of the big aspects of Lego is that you can swap things around, and you can be creative about it, change things as much as you want, basically. So they know exactly which features they need to lock down, and outside of those features that are locked down is basically a free game. That means we can develop these tools here. We can develop some weird one-offs, hats that include hair as well, but we can also give them an entire suit that basically covers up the entire Lego minifigure. But we still know that this minifigure will be able to work with almost any set of Lego that's ever been created because we have this platform, we have these things locked down, essentially. So the formal definition of a platform, shall we say, is basically this collection of elements of these things that we're locking down to form a common structure. And then we can derive products based on that. So we can develop new products with some of the features implemented in order to make, and we can do that very, very efficiently. And basically for manufacturing systems, what we're looking for is this common ground in platforms. So this is the common ground for all the Lego minifigures. This is essentially the commonality between all of them. And what we're trying to find is the common ground or the commonality for manufacturing systems in order to be able to develop new manufacturing systems much quicker and know which kind of things we can change around, because we want the same kind of freedom to move stuff around in manufacturing as they have with the Lego minifigure. The Lego minifigure and the Lego in general is a little bit extreme in that regard, but we want to get there somehow. Okay, so that was basically it for setting the stage. Now we're moving into what I've actually done. This is some of the context, some of the first chapters in my thesis, essentially, where I talk about the background for it. But framing the actual research should give you an idea of how I've approached this problem overall. And it should set up the specific questions I've tried to answer a little bit more precisely, essentially. So first off is the actual the research objective itself, and that is basically to create and apply methods and tools for identifying, developing, and documenting manufacturing system platforms. And the outset I've taken to this is that it should be through commonality and standardization, because that is very important to platforms, that we know what our common ground is and that we can standardize this common ground. The specific approach I've taken to this is something called design science and information systems research. It's basically a framework for conducting research in information science, information systems with a design science perspective. It essentially consists of these three boxes, where we have over here we have the entire environment. So this is the environment that our system or the thing we develop is supposed to be implemented in. So it consists of all the people and the organizations, the technical systems that needs to be a part of, but also all of the issues that we see. So this is where we actually get a prompt for solving an issue into our design science framework. Over here we have a knowledge base where we have the theories and experiences. We have all the artifacts and all the formalisms that we know from previous projects within this field or in related fields that we might be able to use. So this is where we get our founding, basically our foundation for things to actually apply or to reuse. In the design science box itself, we have two basic activities essentially. That is the developing and building, and the justifying and evaluating of artifacts. And artifacts in this case is a catch-all term for the things we actually develop in the design science cycle. So this can be a new model, it can be a new modeling formalism, it can be new theory essentially. But what we do in here is that we continuously iterate between building and justifying. So that means if we develop something, we have to assess it, we have to keep refining it until we're actually satisfied with the results of the artifact. We do this in order to justify the existence, basically, of the artifacts. Because if its existence isn't justified, there's no point to actually having it develop. So we won't actually feed it back into anything. We have two other cycles as well. We have the relevance cycle here, where we get the needs from the environment fed into the actual design science process. But this is also the environment that we actually apply the artifacts, things we develop. We apply this in the environment as well. So we care a lot about actually applying these and validating these artifacts that we develop in order to make sure that they work, that they actually solve the issue we're supposed to solve. In the rigor cycle over here, we basically get our grounding from the knowledge base. So that's all the theories and so on that goes into it. But we also add information back to it. So everything we develop, everything that we have validated, everything we've tried, all the experiences we made, we feed those back into the actual knowledge base in order to further the research as a whole, essentially. And in some cases, such as in mine actually, that we'll talk about a little bit later, there hasn't been a huge knowledge base on the actual field I've been working in. So we've been taking some inspiration from various other fields and started creating a knowledge base on manufacturing system platforms as well. Okay, so moving on to the actual case itself. Well, my project as a whole is affiliated with MATE SPEAR Work Package 2, specifically on modular production platforms, which is very much what I've been working on. And my primary collaborator has been Grundfos. So they're a large Danish manufacturer of discrete products. And in case some of you don't know what Grundfos does, they basically make pumps, essentially, to put it short. And they're pumps both for the private consumer, but also for industrial applications of, a huge variety of sizes and applications, basically. Obviously, I haven't been able to look at every single one of them. I've been looking at a certain subset of them. We started off with mainly circulation pumps, small circulation pumps, specifically the control boxes for circulation pumps. And this is one of them, for instance. So that's about the size we've been working on, the manufacturing of these. And there's been a variety of other products included as well, but this has been one of the main ones throughout the entire process. With that, let's move on to the actual research questions themselves. So I've set up 3 research questions. For each of these research questions, there are 2 to 4 sub-questions, basically. And then I've written a number of papers, and each paper answers 1 to 2 of these sub-questions, and thereby they address the overall research questions as well. So the first research question is basically, how do we develop manufacturing system platforms? How do we document them? And how can we use concepts from software systems in order to get there? So that's what I mentioned, that we need to take inspiration from somewhere in order to go further. And which challenges arise there, obviously. For research question 2, it's basically about how can we classify manufacturing systems and their processes in order to get potential platforms out on the other side. I wrote 3 papers addressing that. And for the last research question, it's basically on how manufacturing systems can be developed by taking into account the existing production landscape. So manufacturers, they always have existing manufacturing systems, and we don't want to necessarily scrap that. We want to make as much as we can of the actual experiences and all the machinery, equipment, and tools that they have for that. And 5 of these papers are published. The last one is in press, so it's still not quite published yet, but it should be fairly soon. That was a very quick run through of the actual approach I've taken. So now we'll get into the things that I've actually been working on in the project, or the contributions that I've actually made. The papers themselves, the way they were set up on the previous slide, they were set up chronologically, and that's the same way they're included in the actual thesis itself. In my presentation, I've taken a slightly different approach because I thought this would make a little bit more sense. But the first one we're starting off with is the actual challenges that we've seen when we've been working with platforms. So I've been working on platforms for quite a while. It actually started during my master's, or actually my second semester on my master's as well. So it's been ongoing for the last 4.5 years. And through this entire process, there's been multiple projects ongoing as well. So the first project that I started working on was basically trying to figure out what are platforms actually. How do we actually can we use them for anything? Because it's something we've heard about, and it seems like it could be useful. But what are they actually? And how do we utilize them? How do we actually develop them? In the second project, started looking more into the actual identification of potential platforms. So we had a bigger scope, we had a bigger group of people that worked together on trying to find out which parts of our manufacturing system should be platforms, how we document them. We started including some co-development as well, since we included people from both the product development department and the manufacturing development department as well, in order to get these two things aligned with each other, because that is very important when we're talking platforms. We need to have these two departments aligned with each other to be able to actually manufacture the things that the product development team makes. After that, we moved on to some more detailed modeling and documentation of platforms. So we took offset in one specific platform, one specific process. Actually, they wanted to make a platform for. Then we started modeling that in detail, and we started documenting it further in order to see what can we actually get from this, and can we create some examples that we can use in the future. On the fourth project, which is essentially my PhD project, it's been on supporting the actual development of platforms and the documentation of them. And it's been through the development of frameworks and tools and trying to apply these in various contexts in order to get manufacturing platforms developed, basically. What we got out of this was a number of challenges that we've been continuously trying to work out at through the fourth project specifically, but trying to address these challenges by developing new tools and new methods to address them. So these are some of the main ones that we came up with. There was a missing consistency and coherency when we're talking about platforms, because people didn't know what platforms were. Every time we introduced a new person, we had to introduce the term platform to them again, because everybody has a different understanding of what platforms are. So we needed a way to do this consistently and do it the same way every single time, so that we were sure everybody had the same understanding of it. That also ties into the misalignment of participant knowledge, where everybody has a different starting point to when they come into an actual project. We also had some miscommunication between departments, because that is fairly common in larger companies where we have multiple departments working on various different things. Well, they had their own objectives by coming into the actual project, and they had their own goals with that. They had their own starting points as well. We had a severe lack of examples and a severe lack of research and tools as well in this field, so we didn't actually know how to approach what we were doing. Because while manufacturing system platforms are gaining more traction, there's still not a lot of examples of implemented manufacturing system platforms. And generally, that's because that's not something that the manufacturers actually want to be public about what their manufacturing system platform looks like, because this can be a huge competitive advantage. And it can allow them, competitors to actually copy their product very, very efficiently. And they'd rather not do that, obviously. So what are the implications of this? Well, the implications are that we need a standardized vocabulary or dictionary for platforms. We need to be clear about these concepts and these elements that platforms consist of, what they can actually do, what they can do for us, and in which case we should apply them. We definitely also need some education to ensure that people understand what it is that we're working on prior to the actual project. But you can spend a lot of time actually telling people about this in the actual projects themselves. We also need more cross-department projects, because that's something that would definitely help the collaboration between the departments as a whole, improve the communication, because there has been instances of, well, the product development team, they have made something that we can't actually manufacture in manufacturing. And we'd rather want to avoid that, because that means a lot of rework, basically. So more cross-department projects could be great, both for co-development, making sure everything is aligned. It could save some time in the long run. And then, of course, we need to somehow develop and apply tools in order to create these examples that we actually need, so we can communicate to people how they're actually supposed to develop manufacturing system platforms. So these are some of the challenges I've been trying to address through this whole project. So one of the actual first things I did as well, in order to get a better understanding of manufacturing system platforms and how we could attack this, was to look into software systems. And you might think, why even care about software systems? This is not what I'm working on, basically. But the simple reason is that with software systems, they are quite a bit further than we are. They can make iterations of systems significantly faster than we can, because we are very much tied to physical equipment still. And every single time we need to make a change at the manufacturing system, well, we have quite a significant lead time. So if we want to get through development processes quickly, well, we got to start looking elsewhere to get some actually tested and applied methods in order to do what we're trying to do. And that's what they're really good at in software systems. So that's why we've been taking some inspiration from them, basically. One of the things that we looked into was they have a lot of architecture, talk about architecture in manufacturing systems as well. We're not going to go massively into architecture, but one of the concepts that we've taken from there is something called the views and viewpoints, basically. The viewpoint is basically a way to look at a specific system. The view you get out at the end is it's basically the resulting look at your system. So it is essentially like this. So a view is to a viewpoint as a program is to a programming language, essentially. So the viewpoint is a collection of ways to look at something. It's basically an outset or a perspective onto something. So an example for this is we're looking at a patch of grass, basically. We have 3 different people looking at the same patch of grass, but they all see different things from it. So the red person down here sees an interesting insect, because that's their perspective on the whole thing. They might be interested in bugs. Whereas the purple person up here sees maybe a flower or the beauty of the field as a whole, whereas the third guy here is just occupied with having to mow the lawn, essentially. So these are very different perspectives on the same actual thing, and that's very important to actually take into consideration when you develop manufacturing system platforms and when you develop the documentation for them as well. Because we want to be able to tailor this documentation and tailor the platforms to the specific people who are looking at them. Because you don't want to give them just a huge stack of papers and have them to read through all of it. If you can just give them the 10 papers that actually fit the information that they need, that's what we want instead. That's significantly more efficient. So in order to do this, well, we obviously took these concepts from manufacturing software systems, but we also looked into another fairly common model actually from software systems, which is the spiral model essentially for development. This is one we developed in order to actually create these views and these viewpoints that we believed we needed in order to create platforms and in order to document platforms. A key takeaway from this is that it has a separate function and technology. So we need to make it clear that there's a difference between the actual function that we need to carry out and the way we carry out the function. And this was crucial in order for us to actually be able to compare all of our manufacturing systems that we have as well. But moving on a little bit, talk about Brownfield platform development, because it's also fairly important to the manufacturer that all the work, all the systems they already have, they don't just go completely lost. And that's what Brownfield does. It takes into context basically the existing environment where you're actually developing your manufacturing system platform, as opposed to Greenfield development where basically everything is up in the air. You have no limitations. Essentially, you can develop almost whatever you want. Obviously, there are advantages and disadvantages to both these approaches. But Brownfield development in particular is interesting because we want to be able to reuse all the equipment that we already have. So the first step to this is essentially a prerequisite to actually starting this whole process. It's not actually part of the Brownfield development approach that I've outlined, but it's the assessment of changeability requirements. So what sort of changeability do we need? How much flexibility do we need? Do we need reconfigurable manufacturing systems, or do we need something else entirely? That's a prerequisite for starting this. It's still included here because it is fairly important, but that's not what I've been working on. After that, we have the identification of platform candidates. So these are potential platforms based on your existing manufacturing system that you could keep working on, keep developing into platforms and base new manufacturing systems off of. That's also a fairly simple process here. You take your existing manufacturing systems, you group them, you classify them, then you end up with a map of your actual production landscape. Based on this, you apply some decision criteria and algorithms in order to identify these appropriate platform candidates. Once you've identified these candidates, well, you go through another series of steps to keep developing them, of course. So for each of these next 4 steps, from 3 to 6, where you basically carry those out for each individual platform candidate that you've developed, that you've identified. And if for some reason you find out during step 4 that, oh, this platform candidate, it doesn't actually make sense to keep developing anyway, well, you can still just scrap it at that point and move on to the next candidate instead. But we go through, basically, we define the essential functions of the candidate. That means what is it actually supposed to be carrying out. We define the principal structure, which there's an example of over here. So this is the principal structure of a robot. This is the actual interesting part, whereas the robot system is what is connected to besides the actual robot itself. So that's a very simple illustration of a principal structure. After that, we go on to define the physical enablers. So these are the ways that our functions are actually carried out, how each of these components are realized in the physical world. Then we move on to actually documenting the platform itself, making sure that people have access to it, the people who need access to it have access to it. Finally, we start with governing and maintaining all these platforms. That's what you do for basically all of your platforms, the whole collection of them that you have. Because we need to maintain them, make sure that they're up to date and that their existence is communicated out elsewhere. And all of these are obviously not rigid prescriptions, they're operational guidelines, so that means there's still some need for flexibility in these. So you can move steps around a little bit, or change, skip a step maybe and go back to it later on. But it's the reason we want to do this brownfield development is essentially that we want to be able to incorporate the experiences from experts and the people who've actually developed the systems and worked on the systems in order to help the acceptance rates of manufacturing system platforms in this company. This one is one of the ways that we've been trying to actually accommodate this step with grouping and classification, because the thing that I started looking into more and more was the actual identification of platform candidates. So I created a consolidated classification scheme, basically for manufacturing system processes or for production system processes, but including the manufacturing processes themselves, also material handling processes where we move stuff around. It also includes some other processes such as test and inspection and control and planning, but we're not going to get massively into that today. The way I did this was basically by searching through a lot of the existing classification schemes that I could find, basically as many as I could find, and then consolidated them into one classification scheme in order to create this comprehensive classification scheme that I could use to classify the processes in manufacturing systems. The end result, as of my paper written, we ended up with these 4 main categories. We had 16 different process families. So this one, obviously, these are split up into different categories. Then we have 53 process classes and 232 process subclasses. And this one is going to keep growing as more processes are added to it and as more work will be put into the test and inspection and control and planning processes, because that's still something that needs to be looked into in this one. But this is just one way to actually describe a part of the manufacturing systems themselves. There's still quite a bit more to it than that. There are a lot of other characteristics that we can't capture just by looking at the processes themselves. So that's why I developed a classification code to actually document or to capture these characteristics. And what we're looking at here is a classification coding scheme which basically describes the system, the entire manufacturing system, both on a system level and on a cell level. So that means the system as a whole, but also the individual stations that carry out the manufacturing processes. And when we're looking at this, at all these things, both with a physical perspective and a logical perspective. So the physical perspective means the actual ways things are carried out, the actual equipment itself, whereas the logicals are more intangible. So that's where we describe certain other things that might have driven the design of the actual manufacturing system itself. This is just a small example of it. The actual code itself consists of 25 digits, where you use one digit to represent a specific characteristic of the manufacturing system. So in this case, the manufacturing system, the reason it was designed was because we had a new product. So we need a new manufacturing system to make this new product. The product itself is fairly small and the production volume is high. We have hardware variety in it, so that means we need the manufacturing system to be able to actually manufacture products with a different hardware variety. And this is just a shorthand for the location of the actual manufacturing system itself. And the classification code basically continues like this. We keep adding stuff to it in order to actually describe. So this basically describes the system, the layout of the system. Then we move on to describe the individual processes of the system. And finally, we describe the actual ways this specific process is carried out. And we keep doing this, adding more and more processes until we have basically an entire block of code that describes the entire manufacturing system itself. So when we have multiple of these, I don't know if they can be seen because of the angle, but when we have more of these code blocks, we can start comparing them to each other. And by comparing these to each other, we can start to locate the actual good solutions or the bad solutions and figure out what actually works in our manufacturing systems. Where have we tried to carry out this process in various different ways? And in which cases has it actually worked properly? There's a lot of applications to this, but one of the key things is that it's very, very difficult to implement in this current state as well. We need to somehow make it a little bit more user-friendly to get a higher acceptance rate on it. But it does take time to implement this, but it can be a very powerful tool as well. Actually, we tried using it in one case as well, where we took 8 manufacturing systems and coded them according to this classification scheme. Then we used 3 drivers based on the frequency of a process or an enabler, how often they occur. Then the prevalence as well, so how many systems they actually occur in, and a ratio between how many different processes an enabler carries out and how many instances there are of the process, and so on. So with that, we got basically a ranking of all the processes and the enablers that were used in the manufacturing system themselves. And from this ranking and from these scores, we can maybe recommend some potential platforms for the future. These are just 3 of the ones we looked at basically. The allocation process up here, which is a material handling process, because it basically scored top in almost everything. We also looked into the robot itself, because it is fairly frequently used as an enabler, and it carries out a lot of different processes as well. We also have the tester, which is used in every single manufacturing system, but there's a lot of different instantiations of this tester, and we want to be able to standardize the way this tester works, basically. That was the end of the actual contributions part, so I'll be moving on to the concluding remarks, because we are nearing the end now. I've tried to answer these 3 research questions, obviously, through my 3 papers, or through my 6 papers. And I think I have gotten around that pretty well. There are some other conclusions that can be drawn based on this, based off of the work I've done as well. So one of the key aspects that I've done in my research is basically the introduction of tools to classify the processes and the characteristics of manufacturing systems. That's one of the key contributions that I've made as I see it. And through customization of this scheme and of this code, you can basically apply it to almost any manufacturer. It doesn't have to be a large manufacturer, it doesn't have to be a manufacturer manufacturing pumps. It can be basically anything, because it is supposed to be flexible in this manner. Because they do deal with the fundamentals of manufacturing, actually. So they're not tied to any specific industry or any specific manufacturer. We also came up with some generic challenges and recommendations that you should consider before you start actually developing manufacturing system platforms, because it is a lengthy process, it is a costly process. There's also an indirect benefit of working with manufacturing system platforms, and that is to get a significantly increased understanding of your actual manufacturing systems. What do our capabilities look like at the manufacturer? And you might be able to get a better grasp on what the production actually looks like around. Future research, there's still a couple of loose ends that could be tied up potentially. This is some of the things that I would like to continue looking into. The first one is actually a comprehensive framework for manufacturing system platform development. This is just an illustration of the elements it could consist of. But yeah, that's basically to make it easier to actually develop manufacturing system platform, figure out which tools you need in which situations. The process classification scheme itself should also be turned into an ontology. That basically means enriching it with certain attributes, certain properties, so we can describe our manufacturing system in more detail based on the classification, and potentially develop some method for saying something about producibility or manufacturability of new products. There's also an app for the actual mapping and the classification of manufacturing systems. We could on whichever platform that we want to, basically, and also an algorithm for actually using this classification code to identify platform candidates. And the actual app and development on this is the subject of a future project as well. So there's going to be some work on that for sure. And last slide, a few acknowledgements. Obviously, I very much like to thank the assessment committee for being here today and for reading through my thesis and giving me feedback on it. Obviously, Professor Mads Jackson from Jönköping is here, and Arne Billberg, thank you very much. And Simon as well, the chairman and the moderator here today. Also like to thank my supervisors, without whom this probably wouldn't have been possible, I'd assume. And obviously Bjørn Langland from Grundfos as well, who's been my main contact at Grundfos. I've had a lot of long discussions about all of this as well. And that was actually what I had to tell you about today. Thank you.
I was a bit worried since I still had 10 slides in my paper.
Yeah.
You printed first, but just in time. All right, so we will have a short break now and start again at 11 o'clock with the questioning from the committee.
Yep.